Good afternoon. My name is Yong from Seoul National University, South Korea. It's an honor to make a presentation here, ATC 24. Today, I will talk about my research, RL-Watchdog, a fast and predictable SSD Liveness Watchdog on storage systems. This research is the result of co-working between Seoul National University and Chung-Ang University. In summary, RL-Watchdog improves the SSD failure detection performance to minimize data loss in the application layer. SSD can be unresponsive by various types of faults, such as its internal controller faults, high temperature, and loose interconnect of PCIe slot. Detecting SSD failure or liveness is an important role of operating systems because the failure makes systems not use SSD. After operating system detects SSD failure, post-failure processes such as data recovery and reboot are required. On the other hand, as more SSDs have utilized on modern huge storage systems, the importance of SSD failure handling becomes much higher. Fast failure detection and notifying application of failure are important because they hasten post-failure jobs. However, the existing Linux kernel has several problems which bother fast failure handling. If failure handling is delayed, failure notification from operating system is delayed as well. It can induce huge data loss because the application can continue buffered write to failed SSD until the failure is notified. Before introducing analysis of the problems in the existing Linux kernel, I will briefly explain how it detects SSD failure. Linux kernel detects SSD failure based on command timeout. For every command submitted to SSD, Linux kernel checks the lifetime of commands to figure out which one has outstanding latency. The commands having excessively long latency are regarded as timeouted, and the kernel aborts the command and resets the PCIe connection to the corresponding SSD. If the SSD is not respondable at the PCIe reconnection process, it is turned into a failed one. According to our analysis, this timeout-based failure detection has three problems. First, accessing SSD is not deterministic in some cases. For example, when applications do buffered write, accessing SSD is triggered by the page cache eviction of the VFS layer. In this case, accessing SSD can be delayed. Secondly, a fixed timeout value is not sufficient. Typically, timeout fitted to latency is required to quickly detect failure. However, command latency can fluctuate by various regions like SSD internal garbage collection. Third, failure notification can be delayed due to the error notification policy of intermediate layers such as file systems. For the first problem, when applications do buffered write, actual command submission to SSD can be postponed by the page cache policy. Therefore, failure detection cannot start even if the SSD has already failed. The graph on the right side shows this problem. We measured the data loss and failure detection time on SSD failure with decreasing the command timeout from 30 seconds to 1 millisecond. Short timeout is expected to decrease detection time, resulting in decreased data loss as well. However, when the timeout is shorter than 1 second, data loss does not decrease and stays at 18 gigabytes because of slow failure detection. The result reveals that delayed failure detection can induce huge data loss with buffered write. As a second point, fixed timeout also bothers fast failure detection. Ideally, the timeout should fit to expected latency of the corresponding command. However, fixed value cannot cover all the cases in IDER because command latency varies by the SSD models, command types, and temporal busyness of SSDs. Excessively long timeout delays failure detection. Contrarily, excessively short timeout can cause false positive failure detection. Even though no failure occurs, the kernel can misdetect SSD failures by short timeout value. In this case, frequent overwriting command can be overhead to application I/O performance as shown in two graphs on the right side. We measured the latency of different command types on two SSD models with changing the command timeout value from 30 seconds to 1 millisecond. In this experiment, SSD failure does not occur. As timeout decreases and false positives occur frequently, the tail latency of commands increases sharply. It shows that the overhead of false positives is not neglectable. As a third problem, failure notification can be delayed in the intermediate layers such as file systems. Even though our failure is detected by the kernel, this failure is not directly notified to the application layer because some file systems notify failure only when its critical metadata I/O fails. To solve these problems, we propose RL-Watchdog. It comprises three schemes: LWW, RLTP, and FFN. First, LWW examines SSD liveness in lightweight and strictly deterministic manner. Second, RLTP predicts command timeout adaptively to SSD states. The last one, FFN, quickly notifies the application of failure regardless of the policy of intermediate layers. The overall procedure of RL-Watchdog is depicted in the figure. LWW periodically submits commands to SSD with the predicted timeout from RLTP. In normal case, after the submitted command completes, RLTP learns command latency and SSD states to increase its prediction accuracy. When SSD fails, the submitted command does not complete within timeout, and LWW resets the NVMe connection to check failure. For the failed SSD, LWW reports failure to FFN, and the application gets an error as a return value of its system calls. The first scheme, LWW, comprises of SSD dedicated threads which periodically submit commands to SSD to check failure. For this usage, we propose a special command, LWLC, which utilizes reserved opcode. All NVMe SSDs handle the reserved opcode with lightweight process. Its handling in SSD only requires checking the opcode and returning the error code to the kernel. Moreover, LWW submits LWLC through the administrator path of NVMe to have lower interference with user I/O commands. To predict the timeout of LWLC adaptively, we propose RLTP. RLTP learns SSD states and LWLC latency online with reinforcement learning to predict future LWLC latency. Reinforcement learning is known as lightweight but hard to predict complex behavior. Moreover, SSD command latency is also known as a hard metric to predict. However, LWLC has a relatively more stable latency than other I/O commands because it does not require to access SSD deeply and is simple to be handled. This characteristic enables reinforcement learning to predict the latency of LWLC. To select features to learn, we measure the correlation between LWLC latency and many features provided by the kernel. As shown in the table on the upper side, the number of in-flight IOs, write throughput, and average write size have high correlation with LWLC latency. Therefore, with these three features are selected to be learned. Then we quantize features to learn quickly and avoid inefficiency, as shown in the table on the lower side. As a result, RLTP can predict LWLC latency with only 384 bytes of memory footprint for one SSD. Lastly, FFN reserves a special flag to the VFS layer to directly notify SSD failure. When LWW reports SSD failure, FFN sets the failure flag and returns an error when the system call comes from the application. It enables quick failure notification to applications regardless of intermediate layers. For evaluation, we use server environment with Xeon E5 to 650 CPU and 160 GB DRAM. Two SSD models, Samsung 980 and PM983, are used to evaluate the impacts of RL-Watchdog in different SSD models. We used 3 SSDs for the RAID array, and to inject real SSD failure, we used a power control board, which enables to control power to SSD independently of the system power. For an accurate comparison, every SSD failure is injected at 2 seconds after the application starts. FIO benchmark is used to generate a buffer to random write, and RocksDB with dbbench and YCSB workload is used to show the impact of RL-Watchdog with real application. We measured data loss and failure detection time to show the impact of RL-Watchdog. Moreover, prediction accuracy is measured to show the efficiency of RLTP on 2 SSD models. On the buffer write, we measure data loss and failure detection time on various file systems with 2 storage configurations, single SSD and RAID 5. RL-Watchdog reduces data loss by up to 82.4% compared to the existing Linux kernel, as shown as red and blue bars in the graph. For the failure detection time, RL-Watchdog reduces it by up to 97.9% compared to the existing Linux kernel, as shown as yellow and green triangles. Interestingly, the application can detect SSD failure on the exe45 system with RL-Watchdog, even though it is not possible on existing Linux. To show that RL-Watchdog is effective on different SSD models, we changed the SSD model to a Samsung 980 SSD and tried the same evaluation again. As a result, RL-Watchdog reduces data loss and detection time to a similar level to the previous evaluation. The result shows that RL-Watchdog is effective on various SSD models. For the real application, RocksDB, we use dbbench and YCSB workload A and update only. On every workload, RL-Watchdog reduces data loss and failure detection time by up to 400,000 operations and 53% respectively. This result shows that RL-Watchdog is effective on the real application as well. To show how much well RLTP predicts LWLC latency, we measured the prediction accuracy on two SSD models. RLTP predicts latency with more than 75% accuracy on both SSD models, and the accuracy reaches up to 99.8%. Moreover, the accuracy saturates within 120 seconds. This result shows that RLTP works well on both SSD models and on various workloads. To show the impact of false positive detection on user I/O performance, we measured buffered I/O tail latency by changing the LWLC timeout policy, such as a fixed one, or using RL-Watchdog. As fixed LWLC timeout decreases, user I/O tail latency increases due to the overhead of frequent false positive detection. Meanwhile, there was no interference to I/O latency with RL-Watchdog because it does not incur false positive detections. This is conclusion. RL-Watchdog examines SSD liveness or failure quickly, precisely, and online to minimize the application data loss with three schemes. First, LWW periodically monitors SSD failures with lightweight overhead. Second, RLTP precisely predicts command latency. Lastly, FFN directly suspends application on failure detection. The evaluation results shows that RL-Watchdog reduces data loss by up to 96.7% compared to the existing Linux kernel, and prediction accuracy reaches up to 99.8%. This is the end of my presentation. Thank you for listening.